Welcome to the flagship freshman seminar series at UCLA called FIAT, and we're super happy to bring you a story about quantum computing, right? We all hear about quantum computing and we don't really know sometimes what it's about. So we're going to give you a little introduction to quantum mechanics, quantum computing. If you have taken a quantum mechanics class before, this is not for you, but you are invited to stay to have some fun. And as the series progresses, we're going to have a diverse cohort of quantum computing practitioners talk to you about their own favorite implementation of quantum computing, about their favorite quantum bit or qubit. This series has been organized by Dr. Ana Valdez-Curiel, Dr. Mike Geer, and by myself. Ana, do you say hi? Introduce yourself and say hi.
I think Anna is on the phone, but yeah, okay, he's now there.
This is Manoj from NRO.
It's the paparazzi. It's the paparazzi already.
Oh, I'm so sorry.
Say hi.
Hi everyone. I'm a postdoc with Clarice here at UCLA. My background is I was doing my PhD working with cold atoms, doing some things closely related to quantum computing, and now I'm excited to continue applying quantum tools to new cool and interesting systems such as living cells and whatnot.
Mark, are you there? Say hi.
Hi, everyone. I'm Mark Geyer. I'm the Executive Director for the Center for Quantum Science and Engineering at UCLA. And I'll be giving a lecture next week on fundamentals of quantum computing. So I'll tell you a little bit more about my background next week when I'm on board. But welcome, and I hope you enjoy it. And it was a real fun to help Clarice get this organized. And I see we've got a whole big group of people on here now, up to around 90 people. That's fantastic. So I'm really looking forward to it, and thank you all for participating.
Do you all see my screen, or do you see it half a screen?
We see your screen.
Okay, let me know if it makes sense what I'm saying, because we are as I'm changing slides. So my name is Clarice Aiello. I am young faculty here at UCLA in the Department of Electrical Engineering. But I consider myself a quantum engineer. This means that I'm trained to develop apparatuses to study and control things that are so small and so well protected from their environment that they're better described by the laws of quantum mechanics, as opposed to the laws of classical mechanics that rule everything big around us and that we learn in school as the laws of Newtonian mechanics, right? Before saying anything, and you continue to see my screen, right? Thumbs up, please, or shout if not.
You're good.
Yes.
Awesome.
Yes.
Okay. Before we talk about quantum mechanics and quantum computing soon, I just want to point out that even if nobody has told this to you yet, or even if you didn't realize it yet, we already live in a quantum world. Many of, or if not most, or if not all technologies around us, they heavily depend on things that are happening at very, very tiny scales that are better described by the laws of quantum mechanics. So we're structuring this very short first class on quantum mechanics around 6 different ideas. Okay? I know that there's a bunch of people in this room, right? I will not have time to take a bunch of questions, but as I present those questions, and if, these ideas, and if there are questions, please feel free to unmute yourself and ask the question. Okay, be brave. I don't mind being interrupted, but we might not have time to discuss everything in detail. So if you all are ready, take a deep breath and let's go into the first quantum mechanical idea that I need to share with you. First of all, I want to let you know that actually quantum mechanics saved the atom. Okay? And it saved the atom by the idea that things that are well described by quantum mechanics can only have certain discrete energetic states. So let me back out a little bit and tell you what was happening at the beginning of actually this century. Sorry, the past century. Oh my God, I'm getting old. In the beginning of the 20th century, the atom was in great, great danger because two titans of physics, they came to slightly different conclusions about what was going on with the atoms and with things in general, right? Maxwell, the guy whom you might have heard about for developing the Maxwell equations of electromagnetics, he discovered that charges that move in a circular orbit, right, they emit light, and as they emit light, they lose energy. Okay, so they are in a circular orbit, they emit light, and they lose a certain energy because some of this energy from those charges got effectively transferred onto the light that is dissipated. However, someone called Rutherford, actually both up to this point, they're all rich old white dudes. Okay, one of the things that we're hoping with this seminar is to bring diversity to quantum physics as early as possible. But Rutherford and Maxwell were both rich old dudes, and Rutherford was studying the models for the atoms, and one of the model that he proposed for what an atom looks like is in this picture here to the bottom left, that says that atoms are composed of negatively charged particles, which we now know as electrons, that orbit around a positively charged nucleus. Okay, a mass, a tiny little mass that is net positively charged. But you can already see that there's a problem there, right? Because Rutherford is saying that the constituents of matter, which apparently, right, they're very stable, they create everything that we can see. If they were to obey the rules that charges or electrons going in a circular orbit, right, like an electron going around a nucleus, emits light, it would mean that the electron emits light, loses energy, and would somehow spiral into the nucleus, right? So how can atoms be stable at all? And it turns out that there's another dude called Bohr that saves the day. Okay, he actually reconciles the observation of Maxwell and the observation of Rutherford by proposing that actually quantum objects, for instance, electrons, which orbit around the nucleus in an atom, they can only occupy discrete energy levels. Okay, this means that while a classical object going into I don't know how to call it, like something where they can oscillate, they can have any position within, like this red stuff can have any position within this glass, right? If this guy were a quantum object, an object well described by the laws of quantum mechanics, it wouldn't be able to explore all the inner surface of this glass. It would only be able to explore certain stable energetic levels. Okay, So this means that a better way to look at the atom, it's still in a gross simplification, would be to have would be Anna, can you maybe try to see who's? Thank you. So one way, a better way of looking at the atom would be with electrons circling, orbiting a nucleus. This is already a gross simplification, but importantly, and as you can see in this middle picture here, the minimal orbit energy for the electron orbiting a nucleus is not zero. This means that whereas, as predicted by Maxwell's, electrons can lose energy and transit to lower discrete orbits, there is a minimal orbit whose energy is not zero. And this effectively is what explains that atoms do exist and do not automatically collapse. So quantum mechanics started by really saving the atom. Now, changing gears to the second idea of quantum mechanics that I would like to share with you. And this idea is centered around a buzzword that people often talk about when they talk about quantum mechanics, and that is wave-particle duality. Okay, by idea number 2 of wave-particle duality, I mean that it's now known because of quantum mechanics that light waves are composed of particles, right, of minimal particles that are known as photons. This is an apocryphal story that I heard about 20 years ago when I started university. I don't think this happened as I'm going to tell, but this image stayed with me, and I hope it stays with you too. It's said, I don't think it really happened, but it's said that one of the people who discovered or who started thinking about wave-particle duality was Albert Einstein, another old dude with whom you might be familiar. It's said that he started thinking that light could be seen as, could be composed as particles in the same, while being considered usually as a wave, right? Because he was looking at a curtain. And in this curtain, he saw discrete sun-faded spots, okay? And by no means this is not scientifically accurate on how that happens, but he was like, if there are discrete spots, sun-faded spots where the light sort of got to those curtains, is it possible that I mean, is it possible that there is something that is discrete about light? Okay, then again, this is just an analogy, which it stuck with me, but it probably didn't happen this way. So it turns out that yes, right? Under some circumstances, light is better described as a particle instead of as a wave, right? For instance, there is a famous experiment that showed that, imagine that you have a metal and light impinging on this metal. And light can have different colors. In the picture to the right, say red, green, and blue. And it turns out that each color of light means a different energy for light, okay? In particular, red light has less energy than green light, which has less energy than blue light. And what was observed in the beginning of the 20th century was that the energy of the electrons actually, so here's what happens. Here's the observation. If you impinged light on a metal surface, sometimes under certain circumstances, electrons were ejected away from the surface. Okay? And people noticed that the energy with which the electrons were flying out does not change if the light beam is weak or strong, if you are in the medium settings or in the strong settings of your flashlight. If the flashlight is in the higher, like in the strong setting, when there's a lot of light coming out, what you might get is more electrons being ejected from the metal. But the energy with which those electrons fly does not depend on the strength of the light beam, but rather on the light color. Okay, and as it turns out, this is consistent with light being composed of particles that we call photons and whose energy has to do with the color of light. An analogy here has to do with the fact that under some circumstances, a tsunami cannot move a coin from across the beach, across the sand, if it doesn't have the right energy, the right frequency. A wave can be very strong, but if it does not have enough energy, it's not going to be able to move the coin away, or the light is not going to be able to eject electrons from the surface. So this is idea number 2, having to do with wave-particle duality. Idea number 3, you might have guessed, is still about wave-particle duality, but it's the other side of the equation, right? It's the fact that quantum mechanics now shows us that tiny particles with mass can also behave as waves. And I'm just looking at this word there. I say tiny, massive. Massive here doesn't mean huge, means that with mass, okay, like an electron. And I think we could all agree that if we have a cannon shooting cannonballs at a wall with 2 slits, right? If we keep randomly shooting those huge cannonballs and then see after the slits on a second wall where the cannonballs end up, right? I don't think it's hard to imagine that we are going to see 2 very definite patterns of where those cannonballs are going to be to have been shot at, right? If they need to go through slits, there's going to be a correspondence between the position of the slits and where the balls end up. And maybe you have seen that something slightly different happens with waves. For instance, light waves. If you put a flashlight through a wall with 2 slits, and then you have a screen at the other end, and try to see where light ends up after going through the slits, what we see is actually very different from the cannonball picture. We see patterns of lightness and darkness that alternate, okay, and are not in a simple or obvious, it can be mathematically described, but it's not in obvious connection with where the slits were. Actually, the spot of largest intensity of light is going to be exactly at a position in between the 2 slits in the leftmost wall. Okay, so all of this is okay and understandable with the laws of classical mechanics until someone saw that if you made the same experiment, but with tiny, tiny particles of mass, such as electrons, under some circumstances, you could see electrons behaving exactly in the same way as light does. In that, if you have an electron cannon and you were to shot electrons through a wall containing two slits and see with the second slit where the electrons ended up, you would see a maximum probability of finding electrons at the position right smack in between the two slits, right? Which indicates that sometimes electrons and other tiny particles behave as waves. And this is not restricted to electrons at all. Right now, 1 year ago, a group at the University of Vienna has shown a similar phenomenon happening not with single electrons, right, but with a molecule composed of about 2,000 atoms, and that's huge. And another point that I want to mention before I forget is that for the electron case, right, described in the top picture here, if you send those electrons one by one, each one will individually arrive at one particular location. And even though it doesn't talk to other electrons, if you bombard many electrons that do not talk to each other, it will be so that they will rearrange themselves in a pattern that would follow waves. So that is super cool. And actually, there's another analogy for electrons behaving as waves in that if you confine electrons, for instance, electrons within a atom, they are sort of confined to the atom. The way you describe the energy levels of this electron has to do with waves. Okay, and the idea is that the electrons, as they increase in energy, they are associated with a wave of increasing energy in the same way that we have increasing energy for notes going higher and higher in pitch. And yes, that's a left-handed guitar. Okay.
Question?
Yes, what are your questions right now?
How does the wavelength of an electron compare to the wavelength of light? So if you have like a 1 keV electron, how would that compare to light?
Anna, do you want to tackle that?
Yes, let me do some quick calculation and I can tell you. But essentially it will also depend essentially on how, well, you already gave me a number, MeV. So I unfortunately don't speak the MeV language really well. I speak Hertz, and but let's have a quick look.
But in general, how do the energy, like, well, there's no in general. You're absolutely right. Sorry.
1 MeV is equal to oh my goodness. let's jump to next question, and I promise I'll have a number for you in a minute.
Next question. Before it gets weirder. It's going to get way weirder, so keep the questions coming.
Okay, so I forget what it's called, but why is the I've heard of the thing with the metal absorbing light, and it depends on the frequency, like rather than magnitude. I don't know. But why is that evidence for a light behaving like a particle?
So what is the best way to answer that? Like, apart from the fact that you can only, so why, okay. So maybe Mark or Anna have a better explanation, but to me, the fact that, so we get more electrons out for a fixed color, right? If we increase the intensity, also means that if there's a direct relationship, it might mean that, I mean, there are more particles of light interacting with the electrons. Anna or Mark, how else do I answer that? The fact that one can play with single photons in the laboratory?
The reason for that is actually that the higher the frequency, the more energetic the light, the more energetic the electrons that are released come out. So that's a simple answer to that. The greater the intensity, the greater the number of electrons, but the higher the energy of the electrons.
Which is the result of this experiment?
So I had promised I would have an answer for previous question. And so just to give you an idea of scales, the spectrum of light from say UV to infrared goes something in between 120 electron volts at very near infrared to something about 1 electron volt at infrared. So that is, you were asking how that compares with mega electron volts or milli electron volts. Well, I think in general, for things that are not moving too fast anyways, the wavelength is tiny. Or did I get it the other way around?
Okay, so for something moving fast, the wavelength of an electron would be a lot less than the wavelength of light.
I think so.
Yes, that's right. There's a technological implication for that, and it has to do with how patterns can be written in fabricating semiconductor devices, for example. Most of the devices that are made now that go into your cell phones and computer chips and things like that, the standard Intel processes use just light, very short wavelength light in order to write very small features, but nevertheless it's mostly optical. you can write even smaller features if you use electron beams. And so there's a whole technology called electron beam lithography that enables you to write much smaller features than you can write with optical lithography. And it's due exactly to this fact that the electron wavelength is smaller.
So I'll go on. We're almost there because now it's really going to get interesting.
Professor, I just have one thing to mention. Someone just texted me saying she's in the waiting room and if you could let her in. Sweet,
Yes.
thank you.
Yes, sir.
Done. Sorry, I got distracted answering question.
So the idea number 4 has to do with the concept that you might also have heard of superposition. I apologize, you might pick up the sound from the construction there. Sorry about that, if you do. Anyways, but you might have heard of something called superposition, right? A property of quantum objects called superposition, which means that a quantum object can be in a superposition of energy states. Okay? Exploring the picture that we were talking about before, about electrons orbiting an atom in different tracks, okay? Superposition says that a single electron can be, for instance, orbiting 2 different tracks at the same state in time, at the same time. Okay, it's not that the electron is switching between tracks, and those tracks here in the top left picture are shown as a track related that we call 0 and a track related to called 1. Okay, for reasons that will become clear. But the idea is that this electron at the same time is in orbit 0 and in orbit 1. This means that at the same time, it has characters and that have to do with orbit 0 and a character that has to do with orbit 1. Okay. And there's a reason why I called the orbits 0 and 1, because I would like to make an analogy with with what goes on in computers to set the stage for Mark and for the other classes in this seminar. I think you might be familiar with the classical bit, or the way that your laptop, your phone processes information, which in a very simplified way means that there are units processing, there's information transferred between the different components of your device in the forms of 0 and 1. And 0 and 1 here meaning different states of a physical parameter. For instance, those numbers are not accurate, but a state 0 is represented by a voltage sent of 0 volts, and a bit 1 is represented by a voltage, say, of 5 volts being transmitted. And interestingly, a classical, well, not interestingly, like obviously, a classical bit can be in 0 or 1. You can send the information either as 0 volts or 5 volts. So in the sense, the classical bit is like a binary switch. Quantum mechanics says that it's possible to do a little bit better computation by using quantum objects as bits. Those quantum objects used as bits are called quantum bits or qubits. Okay, so 1 qubit could be, for instance, 1 electron in different energy states. That is 1 electron that can occupy different tracks as it goes around the atom. What's special though, because a quantum object can be in a superposition state, is that we can actually experimentally tune in a non-binary way, like as dials, different compositions of this quantum bit between the two tracks. We can, in other ways, tune how much character 1 the electron has and how many character 0 the electron has, like continuously. Okay? Which is very unusual. We do not see this in our big world, and there's a reason for that. And the reason has to do with the 5th idea that I would like to share with you. The idea that measuring a quantum system makes it classical and sort of takes away all the nice quantumness about it. Okay? So what this means is that even if one can make, or even if a quantum object can be in a superposition of energy state, that is an electron in the 0 track and in the 1 track, when you put an apparatus there to observe it, imagine that you want to measure the energy of the electron, right? What you get with your meter, your energy meter, is always 100% of the time that you take a measurement on any electron, you will only see either 0, the energy associated with 0, or the energy associated with 1. This means that if an electron were a coin and the electron could be in any, the coin could be in any superposition, combination of energies for for the two sides of the coin. Once the coin it gets to the ground and gets to a surface, we get definitely one side or the other. This is also what happens for quantum objects. And then you're like, but that doesn't make sense, right? Because this means that how can you observe quantum states, right? In this case, if all that we are observing are states that do not show any superposition, or it's just states that you would expect to find in a meter. And to answer that, I would like to introduce something that has to do with statistics, right? So in order to measure a quantum state, if you can only perform the measurement once, you're toast. There's no way you can tell anything about the quantum state of an electron in an atom if you only have access to 1. But what one can do is get many identically prepared electrons in an arbitrary superposition state, or you can perform the experiment in one electron many times. You prepare it in a quantum state, observe it, measure its energy, then prepare it in a quantum state and measure it again, so that on average, the energy, the final energy that you measure for this electron is going to be somewhere between the energy related to track 0 and to track 1. And this is actually key to how people do any quantum experiments and also quantum computing experiments. What are your questions right now? I have one more slide. Actually, I have 2 more slides. So I would like to pause for questions because I know it's getting weirder and weirder.
Clarice, this is Manoj. Could I ask a question, please?
Yes.
Yes. I mean, could you look at this, of the statistics, as the probability of this electron being in track 1 and track 0? So when it's exactly in the middle, it's 50-50. But assuming it is 51, 49, or any fraction thereof, you're pushed to either 1 or 0. So I mean, of course, it's a superposition of many of these things. But when you take a snapshot of that, you find that deterministic state of either 0 or 1. Could that be one way that we can look at it?
Well, that's sort of exactly what happens. I'm not sure what you mean by snapshot. What I understand when you say snapshot is we're trying to measure it, right? When we measure it, when we try to take a snapshot, try to learn something about it, we will always get one side or the other. We're always going to get the energy associated with 0 or the energy associated with 1. For each electron, that's what we're going to get.
So let's alternatively think, what if the electron was exactly in the middle of 0 and 1? I mean, it's just a very simplistic way.
Yeah, it is well described by the laws of quantum mechanics for as long as nobody tries to measure it. And what we're going to see is actually just being around atoms can also have the same effect. As long as the atom is quiet and not interacting with a lot of stuff, it is like this electron will be well described by the laws of quantum mechanics. But if one wants to actually measure the energetic state, or which is equivalent, when this electron or this atom starts interacting with bunches of atoms in a lattice that all vibrate, this is also a type of measurement. And this is also the reason why everything that we see around us, big, right, is classical rather than quantum, even though each component, if isolated at the tiny, tiny little level, is well described by the laws of quantum mechanics. So every time you take a snapshot, you will only find it, you will only be able to see it in a well-behaved state, right? It will be absolutely well-behaved. We can only infer like the type of superposition, say half in one, half in the other, because as you build up statistics, statistically, the electron will be measured in 0 or in 1 at a fraction of time, at a fraction of times that corresponds to this sort of ratio between the superposition states.
So in a way, if I may continue just one more question and then I'll stop, is so one could look at oneself, say, for example, you or me, as all these electrons, assuming all the proteins and carbohydrates and all in our body, as comprising these electrons. But when you look at yourself or me, we are seeing this snapshot of this deterministic thing. We are not seeing all the electrons in this this probabilistic orbit, say, states. Could that be one way to describe?
Yeah, the idea is that the classical word, and maybe I'll go to one slide, which has to do with loss of quantumness, right? Why we see you and me as big, hard objects that cannot be in superposition, but why don't we ordinarily see macroscopic quantum effects, right? All I want to say is that everything that starts quantum dies classical. And I've just mentioned that measuring any quantum system in any non-trivial superposition state is going to yield a expected or classical result. So that First of all, to see quantum mechanical phenomena happening, you need some sort of probabilistic averaging.
Thank you.
The other thing I would like to say is that the things that move around us, right? Everything is at room temperature, which means that our molecules are vibrating really, really fast. And this process helps to make us, it increases the loss of the coherence character of things. Okay, this is also known in jargon in the quantum sciences as decoherence. You are losing the quantumness of something by decohering. And I think it's important to point out that the world we live in, one of our proteins sitting together with the next of our proteins helps in that one protein is forcing the other out of like a good, long-lived, observable quantum state. Okay? In this way, in the same way that if we try with an apparatus to observe the state of the electrons by measuring its energy, track 0 or track 1, in a way, our own things, our own proteins and things happening inside our body or our cells or everything, they are measuring each other. They are interfering. They're messing up with the quantum character of each other. I don't have a lot of time to talk about this much, but loss of quantumness is one of my favorite topics.
I mean, that's perfect answer. Thank you, Clarice. Thank you.
And without further ado, I would like to refer to another very, very big buzzword that you might have heard called entanglement. Okay? And I have a quick video to show to you. And the idea, and I'll explain, is that two quantum objects are entangled if when you learn something about one, you learn something about the other very much, in quotes, instantaneously. Okay. The first thing that I want to say is that I don't like the word instantaneously. You might know that nothing happens in the universe, to the best of our knowledge, faster than the speed of light. So instantaneously is like a weird word to use here. And I assure you that entanglement does not affect causality, does not happen faster than the speed of light. The other thing I need to point out is that entanglement is not some weird communication or force between quantum objects. Okay, entanglement is not voodoo. Entanglement is absolutely scientific, and sometimes there's an aura of bizarreness around entanglement. Okay, don't go for that. In order to explain entanglement with a quick video, I need to make a small analogy that's also going to be explored in the video. Imagine that you're given two closed wooden boxes, and you're told that, well, there are two balls in these closed boxes, right? One is red and the other one is green. And then you say, okay, imagine that you open one of the boxes and you find that you have a red ball. What this means is that instantaneously, it's the nomenclature is I don't like it. Instantaneously, you know that the ball in the other box that remains closed must be green. If you observed by opening the one box, if you observed the red ball, you know, because of what you were told, that there was one of each, you know that the other one, there's a green one. And let me share with you a tiny little video that explains what entanglement is. Oh my God, I didn't make a sound check. Can you see this YouTube video?
Yes.
Yes, okay. Can you hear the sound? Let's see. Did you hear something?
No.
No.
Yes, I screwed up. So let me try to change the Zoom configurations. And I think that by now we are all familiar with Zoom glitches, which makes our shared humanity very shared. So, speaker, analog stereo. Do you hear something now? No?
No.
Do you hear me? You hear me?
Yes.
Do you hear
Yes.
anything now?
No.
Sorry. Do you hear it? No? Nothing? So let me see. I think it has closed captioning. So you see my screen, right?
Yes,
It's
Not
Clarice.
anymore.
No, no, I'm sorry, no. I think, Clarice, that you have to share the screen first.
Oh, the screen is not shared. You don't see my
Yeah,
screen.
yes, you need to share the screen first, and then you can share the sound.
You see the YouTube video displayed there?
Yes.
Yes.
Okay. So if you do not, we can share this this video later, and I think there is a closed captioning. So apologies in advance, but let's put it 20 seconds back. Okay, 10 seconds of this video.
Even particles physically separate into each other instantaneously. The experiment is called a
The theory implies tiny particles like electrons or photons can be in different states.
being represented by red and green. But in the Bell test, the two particles are entangled, which means that when one particle is green, the other has to be red, and vice versa. Now, quantum physics says that both particles actually exist in both states at the same time. That is, until you measure them. And if they're entangled, when you measure one of them, the other will also instantly resolve into the other state. It's as if the distant particles are somehow influencing each other faster than the speed of light. Sounds impossible? Einstein certainly thought so.
Oy. And the point is that Einstein was, and you see me and you hear me, right? And the point is that Einstein was wrong, okay? Nothing happens faster than the speed of light, and entanglement can be explained, seen in the lab without violating any good established laws of physics. I think this sort of concludes our very, very short and sweet talk on fundamentals of quantum mechanics. So the only thing that I think I personally hope is that this might have whet your appetite for you to take other and further quantum mechanics courses, right? we hope that you come back for Mark's lecture next time on fundamentals of quantum computing. And we hope you come back for quantum computing practitioners, among which Anna. They come explain about their own favorite qubit or quantum bit. I think we're officially at the end. Thank you all for showing up. And I think we have this Zoom room for another half an hour or so. And we are happy to take your questions and tell us how you feel about that. And we're happy to give you, if you want to learn more about quantum mechanics before next week, we can give you recommendations of books, or let us know. What did you guys think? Tell us.
Hi, Professor. Could you hear me?
Yes, please call me Clarice. Yes.
Yeah. So like this introduction class is very interesting, and I'm quite interested in this topic as I'm a computer science major student, and I'm quite interested in quantum computing, but I don't think I have a very good background in quantum mechanics, as I've not taken many physics classes. So this is quite a good introduction. And I would also like, I'm curious, like, is there a official website for this course where you would post the materials?
Yes, but not happening like soon. We hope to link all of those lectures to our group's channel in YouTube, and also the Center for Quantum Science and Engineering at UCLA has their own YouTube channel. So if you have registered, and you who are here have all probably registered, I think we have your information, and we will contact you once we decide exactly what to do with this cool series.
Yeah. So yeah, it will be a good idea if you like would email us again and introduce us, maybe give us a link to maybe your YouTube channel or anything.
Yes,
yeah,
we will. And I just need to make a comment in that you already have the background that is necessary to take quantum mechanics. Okay, if you follow your regular required introductory physics courses, you will be good to take quantum mechanics. There's nothing special about quantum mechanics. There's nothing magical. And don't feel intimidated. And I hope to see you in one of our quantum courses. Next semester, next quarter, I'm actually teaching a new course on quantum mechanics for engineers in the electro engineering department. And yeah.
Okay, thank you. And I have a specific question regarding the previous slides. So you said that once you prepare a superposition state and then you measure it, then it will fall into one of the classical states. And if you only measure once, then there's no way you can determine the property of the superposition state. So you have to take multiple measurements. But after one measurement, you have to set up the superposition state again. So how would you make sure that the second time you set up this superposition state, you end up in the same superposition state as the first superposition state?
Anna, do you want to tackle that?
Sure. I mean, honestly, this is a question that, people who are professionally working on quantum computers are still working on, like having reliable state preparation. You can try to control all the parameters that go into making the superposition as well as you can, but still it's challenging to make exactly the same state.
And I think like a little bit like even before, because Anna is an expert in playing with quantum states. I think that what can be said here is that quantum states can be manipulated, prepared, steered in the lab using excitation with electromagnetic fields. Okay, so go Anna.
No, I mean you're absolutely right. I skipped to mention that very important fact that I mean you have your 0 or your 1 track. I can apply some light, for example, that has the energy that matches that 0 to 1 energy difference, and depending on how long I shoot my light on it, I can make it go all the way from 0 to 1 or stay somewhere in between, depending on how strong my light is or how long I shine it on. And it has to be this light has to be very carefully calibrated, because if the intensity changes a little or its color changes a little, like I will not be preparing exactly the same state, but I can try my best.
Okay. And so what properties or what parameters would you use to describe superposition states? Like how is one state different from other states?
Well, I guess one way, I don't want to get super technical, but maybe I will just now. I guess you can think of all quantum state, all the superpositions of two states like living in the surface of a sphere. So every superposition represents a different point on the surface. And that just means like how much of this A or B parameter you put in. So how much 0 or how much 1 you add lands you on a different spot on the sphere. And that for me is an easy way to visualize different superpositions.
Okay, thanks.
Does anyone have more questions?
Oh, I actually had a question. So I'm kind of new to the concept of quantum computing and I'm a math major. So I was kind of wondering like, what are the applications of this kind of like area?
Well, something that is very, I think one of the like biggest applications that make these very attractive to people are things like factorization of prime numbers. I think the algorithms that typically do this like on your regular computers take exponential time to factorize, and then there's equivalent algorithms for quantum computers that can do so in, I believe it's polynomial time. So that, of course, becomes very attractive. There's other things like in things like cryptography, there is some things in quantum that you cannot copy a quantum state, so that gives you some protection against people stealing your information. That also makes quantum computing very attractive. And just, I guess, in general, if you think of a classical computer, every operation you do, you are like 0 plus 0, 0, 0 plus 1, 1, 1 plus 1, 0, and so on. But with a quantum computer, you put in 2 superposition states and you get all the results out in like one run. So just this like parallelizing of calculations makes it very powerful.
Thank you.
Oh, I have a question. I'm not really sure if I understand entanglement, specifically why it was a controversial idea, because like you gave the example of having like 2 balls, one is one color, one is another color, and putting them in boxes. And obviously like intuitively, we all understand that if you open one box, no matter how far away it is, you'll know what was up with the other box. So like that clearly isn't like transmitting any information faster than light. So like, in what way is the quantum example, in what way could that be like construed as like somehow like doing something instantaneously? Like what's the difference?
Yeah, shall I continue answering? Yeah, no, this is a very good point. It gets, I think, a little tricky and subtle. This, like, I guess the underlying thing in this ball experiment is that we knew that the ball was red or green to begin with, but in these quantum states, when you're in a superposition, well, it's not well defined, and only when you make the measurement, it gets defined. So it's like you don't know if you're red or green. So I guess one particle deciding that it's red makes the other one decide that it's green instantaneously. I don't know if this clarifies your point at all. It's the fact that the state is not well defined before the measurement. And then you can do things like, how can I make it not sound confusing? You can measure in a different color basis. Or yeah, like you can observe if the ball is red or green in one measurement, and then decide that you want to measure if it's, I don't know, hot or cold. And sorry, this is getting way too confusing, but
I think that's proof that I mean, it's not that it is confusing. I mean, it's just that we still live in a classical world and we have trouble grasping how to explain things that we know happen at the quantum scale. Maybe, but I'll shut up. Continue the explanation. Sorry.
Yeah, well, one thing that I should also point out is that even if you get this like faster than speed of light information transfer, there is proofs that this information, this cannot be used to transfer useful information. You always need like classical communication channel. Like even if this was red and this was green, someone will have to call someone on the phone and say, hey, I measured green, before that information can be used. And this is what is done in some things called quantum teleportation, where they use these entanglement properties to transfer the state of one ball to another ball. But you always need this classical, slower than the speed of light channel for the communication to be useful.
And quantum teleportation is not the Star Trek beaming. In quantum teleportation, there is no transfer of matter. There's transfer of information. Sorry. Right, Anna? Do you agree with this?
I agree.
So I have a comment, not a question, but earlier on discussion on the history of physics, the old white men. First of all, James Clerk Maxwell died in his 40s. Albert Einstein in his Annus Mirabilis was 26 and quite poor, working as a third-class patent clerk. So Einstein became an old white man, neither rich. There is history of that, of Cavendish being an old rich white guy. But yes, they were old guys, and the concept of white also really didn't exist back then. All that said, the inclusion of many underrepresented people is a very good thing, but just for the history of science.
Point taken. I'm sorry. We'll be incorporated next time.
Got it.
I don't want to hog the questions. Does anyone? But I do have another question if no one else wants to ask one. Okay, I guess I'm just gonna ask a question. So like something that like I kind of get heard thrown around is like people talking about different like interpretations of quantum mechanics, like you hear like Copenhagen interpret, or is it Copenhagen? I don't know how to say that. You hear things about different interpretations, and I was wondering, as part of this class where we're talking about different people's favorite like methods of like doing quantum computing, will there be any discussion of how people actually like the interpretation stuff? Like how do people actually think about what's going on? Or is that, you know, I don't know. Is that a part of this class or not?
Mark?
Yeah, I think probably not, in the sense that, you know, most people are going to be trying to just explain fundamentals of the particular type of qubit that they're working with, and how they you know, measure it and do manipulations of it in the laboratory. I'm not sure exactly what your question is, in the sense that there are different when you talk about the Copenhagen interpretation and such. There are some very sort of concrete differences in the way you can think about the mathematical representation of quantum mechanics. That's a separate issue from these really foundational questions. And there's a whole sort of subfield of quantum foundations, and that existed before quantum information science. It's been probably enriched due to people thinking about quantum information science, but that's a very, very deep subject, and that's not likely to be touched on by many of the people that are talking here. Most people are pretty practical, and they've got something in the lab that they're trying to do, and they're not thinking about these sort of deeper questions. But so I would say probably no, that those kinds of questions aren't going to be addressed in this class. They're very interesting, and they're very deep, and they're very profound. And I encourage you to go off on your own and explore that a little bit if you want. And you know, there are probably courses that are taught on that, but it requires a lot of background.
Okay, thank you.
I have a question about how entanglement relates to electrons.
Sorry.
Yeah, sure. Go ahead. What's the specific? Do you have a specific question?
No,
Or-
just in general. Because you're talking about how quantum objects are entangled. So how would that work with electrons, like generally?
Well, I can give you a specific example of how electrons get entangled, and you'll probably hear more about this in 2 weeks when Jason Pettit talks about electrons and quantum dots and how those are used for qubits. So, for example, if you take 2 electrons and you confine just those 2 electrons in some kind of a potential that allows for, you know, only those 2 electrons to be interacting, those 2 electrons go into what's called a singlet state. And that singlet state is an entangled state, and so that is kind of the simplest way. There was a question about how do you reproducibly generate entangled states. That's a good example of a way with electrons, because anytime you put these two electrons into a confined space where, again, they're the only two particles interacting, they always go into this singlet state. And so that's always a known superposition. Yeah, so electrons can be entangled in that fashion, and you know, you can do more than two, and obviously it can get much more complicated. But it's possible. I mean, what you'll hear about in the quantum dot stuff is that you can form that entangled state by putting two electrons in close proximity in, say, a single quantum dot, and then you can move one of those electrons further away, and they stay in that entangled state even as you separate those electrons. And you can take this to the limit of the communication applications that we were talking about. And you can think about moving that electron really, really far away, not just, you know, maybe a few nanometers away or a few hundred nanometers, but a few hundred meters away. And it still stays in that entangled state as long as it's not interacting with the environment and subject to decoherence in some way.
Okay, thank you.
A more general comment, I was going to make a more general comment about superposition. I think it's easy for someone who comes at this with you know, hearing about it for the first time to somehow think that that everything is always in a superposition state. That's not necessarily the case. I mean, if you prepare a system in what's called the ground state, which is the lowest energy state, that's a particular state that particle is, or that system is in. You can measure it any number of times you want, and you're always going to measure the ground state energy for that. So I think it's as exciting as it is to talk about superposition. We shouldn't get caught up in the notion that everything sits in a superposition state of some kind. You can prepare states that are not superposition states, and then you can put them into superpositions and manipulate them. And based on how long they may be interacting in that superposition state, you can have a known state at the end. And so not everything, you know, there's, I think, a tendency for people to think that, oh, quantum mechanics, everything's probabilistic, but that's not really true. You can prepare states in a known superposition state. You can do a manipulation of those, and you can read them out, and you can know what that is with 100% probability if you've manipulated the state in the right way. So not everything is completely random. And quantum computing wouldn't actually work if that was the case. I mean, one of the whole premises of quantum computing is that you know precisely how to manipulate these states and get them into a state at the end of the application of some number of quantum gates that actually gives you a deterministic answer to the problem that you're trying to solve.
To just follow up on that, I mean, isn't it a fact then that, I mean, of course, it's all probabilistic, but since we are able to then make it deterministic, I mean, that's, we will be creating this really powerful, say, medium or means to do these things. But otherwise, I mean, even at absolute zero, wouldn't there be some probability to the existence of a state? I mean, is everything, even at ground state, is it entirely deterministic?
Well, I mean, so the Heisenberg uncertainty principle still applies, right?
Right, exactly.
So, but that doesn't preclude you being in a known state, right? I mean, so the example of where the uncertainty principle comes into play would be, say, a case where you're changing the system in some particular way over some period of time. And what the Heisenberg uncertainty principle tells you is that there's some uncertainty in the energy based on how long the time the system was subject to interaction. This is this delta E delta T constrained by H bar. And so that does tell you what kind of uncertainty there could be, you know, in the energy of the system, for example. But that's a different concept than really being in the ground state and knowing what that state is. So I don't know. That's maybe not the best explanation of that, but maybe someone else can chime in.
Well, exactly. I mean, I completely get what you're trying to say, but because I was the other day reading a book on Einstein, and it looks like even he had, say, he didn't really buy this uncertainty or this, even though he was the person who actually pushed the whole field into that state towards his end. He was almost completely against Planck and say Heisenberg and all of these things. I mean, it is a hard conceptual problem, but you're absolutely right. I mean, unless you can get some sort of a ground state or a measurable state, then I mean, all of this will be only in dreams or in concept. We won't be able to do something useful. But right. I mean, not to say that what you said is contradictory, but I mean, I'm trying to say is maybe that's the simplest way that can, in some ways. Thank you.
So I have a question about like this quantum computing's applications to the pandemic, because I was reading an article, or not an article, I was reading a paper trying to understand it because I'm just a first year, so I had trouble understanding it here and there. I read it around 2 weeks ago, and it was about quantum dots and how they think that might be promising as a therapeutic and therapeutic for the COVID-19 virus. I went because it came out in May. I'm not sure if about how it's going, but how promising are quantum dots to inhibit the COVID-19 virus? Because I read about it and it was published in May, so I'm just curious, are they going anywhere?
I mean, if I may answer that, since I saw one of the talk on that. I'm from the Naval Research Lab, by the way. One of the researchers is from here, so it was published in ACS Nano, which Professor Paul Weiss is at your place, is the chief editor of that. So what they did is they used the quantum dot as the center of the COVID virus, and they attached to the quantum dot these spikes that you see for the virus, and to infect or to mimic the infection of a cell at the ACE2 sites. And just from the sort of changes in the fluorescence or the quantum states of this quantum dot, they were trying to then figure out as to where exactly the spikes were attaching to. So they did have a very good means to find that. But then, of course, there are more biological questions as to does that make the spikes, does the structure of the spikes change because it is attached to the quantum? I mean, there are many things that can be asked, but I mean, you're right. It was a really nice piece of work. And the main author or the corresponding author was from NIH. Thank you.
No, thank you. That was a really good answer, because I was just curious, how that paper was kind of helping out this field, because I'm not really too much familiar with this field. Again, I'm a first-year biophysics major, and this stuff really fascinates me. I do want to go into the future. So thank you for.
I mean, that's where I believe Professor Aiello probably would know much more about the quantum physics in terms of neuromorphic computing and synapses and things like that. Because at the end of the day, we as human beings are, again, this sort of a probabilistic system. This is my belief. I could be entirely wrong. But then as we are speaking, we are coming up with some sort of a deterministic sort of actions. Though as I'm speaking with you, I don't know what I'm going to speak to you next, but still, when I've spoken the word, it is a deterministic sort of answer. So it is really fascinating.
Thank you.
We had a question before about applications. I just wanted to mention, I'll talk a little bit about that next week. I'll make sure that gets included in the section talking about quantum computing. I'll discuss some of the applications in a little bit more detail.
Thank you.
Hello. I have a logistic question for the professor. So first, how long does the lecture usually last? I'm asking this because I'm actually having a time conflict. I'm a UCLA student, so like I'm taking other classes, and I'm a time conflict with a discussion which is actually also taught by the professor. And I wonder if it's possible that I can like fit both classes into the schedule.
So the class officially is from 9 to 9:50.
Okay.
But I think that we and the further speakers, we might just be here a little bit longer just for people who might want to talk to us. Can you see my screen now?
Yes.
So
yes.
I just wanted to actually point out what we have in store for all of you. And this is shaping up like super nicely. So the lectures themselves are going to be 50 minutes long, but I think we're all happy to stay here for a while. And I think it might be time for us to be leaving to Anna and Mark. Final remarks?
So I'm just a second question. Is it possible to like actually enroll in this class? Because I found this class, but it says the class is full and I'm not enrolled in. So I wonder if it's possible to get a PTE.
Yes, yes. Send a message. Yes, send me a message. Send me an email, and I'll
Okay.
Yes.
Okay, thank you.
I have another logistic question related to that. Like, I couldn't even find this class on like my UCLA class planner. Like, is there a course number related, like associated? I just couldn't find it.
I don't know a lot about logistics. All I know is that if you put FIAT Lux seminars, there's a list of seminars, and I think there's a number that is associated with it, and I can tell you it in a moment. Are there any other logistic questions?
Oh, and if I enroll in this class, would there be like would there be like homeworks or exams or?
No, we want you to have fun and to learn about quantum computing. So I'm in CCLE. I see it described as FIAT Lux freshman seminars, NGR, so ENGR 19-2-Aiello, which is my last name. That is all I see.
Okay, so I might also like email you and get a PTE to get in.
Go for it. So I think we really need to go. Anna and Mark, final remarks.
I actually just got emailed. I wish I'd noticed it earlier. A very nice graphic about the about wavelength for different particles and light and things like that. Do you want me to share it? We're kind of down to only a fifth of the number of original people, but I can try to put it on my screen.
Oh, I have to stop sharing.
So let's see. Let me see if I can open this up, and I'll share my other screen over here. Okay, so are you seeing my screen now?
No, not yet.
Not yet. Desktop 2. Oh, desktop 2 share. There we go. So are you seeing my screen now?
Yes.
Yes.
And are you seeing the diagram?
Yes.
Okay, yeah, so this was, actually this got sent to me by Adam Stieg, who's the director of the CNSI. I think his associate director of the CNSI. He was listening in and he sent this. I wish I'd have noticed this earlier. So anyway, this just shows the wavelength for some of the typical electromagnetic spectrum, radio waves being quite long. Microwave's a little bit shorter than that. Then you go into infrared, ultraviolet, and then you can see you get to the particles like electrons, protons, et cetera. And of course, this is on a logarithmic scale. So, you know, we're going in powers of 10 in wavelength. So this is a neat diagram. Maybe we can figure out a way to share this on the some kind of link for the class. But yeah, this kind of shows where you're at. So the comment that I was making about lithography is that optical lithography has been operating in the UV and the short, very, very short wavelength UV, and that gets you to a particular length scale for being able to pattern features. But you can see you can do much better if you go down to using electron beams instead of optical waves.
Mark, if you send this to me, we'll find a home.
Yeah, I'll forward this to you. Okay, yeah, the only other thing I'll say is I hope you stick around for next week, and we'll talk more about, get more into quantum computing. I'll probably be repeating a few things that Clarice said today in a little bit different context, but I think that's probably not bad to repeat some of the concepts again. And then we'll go more into how we actually use qubits to do quantum computing, and talk a little bit about where we are in terms of quantum computers in the present day, and then a little bit about what the future may hold for larger scale quantum computers.
Emma?
Well, I just want to say that I am jealous of you guys who are getting to learn this for the first time, because I think it's a super cool and fascinating project, and I hope you learn a lot and you get a lot out of from this, and we're looking forward to seeing you again.
See you all next week then. Bye-bye.
Thank you.
Thank you. Bye.
Bye.